Okay, so now we're going to talk about all zeros. We've talked about the real ones, so which ones does that leave? Well, it leaves our imaginary or complex roots. So let's take a look at what we're doing with this. So the fundamental theorem of algebra says that every polynomial can be factored over the real numbers into a product of linear factors. So that's examples like x minus 2, because it's degree 1, so that's a linear factor, and irreducible quadratics. We know this is a quadratic factor because it's degree 2. Okay, and so that's really interesting to know. Gauss proved that the fundamental theorem of algebra, all polynomials can be broken down into linear factors and irreducible quadratics. So if we get it to where it's got 4 terms in it, we know that it will in fact factor further. So that's good to know. All right, so even though we have a polynomial factored like this, we know that that irreducible quadratic actually can be factored if we use complex numbers, right? If we set that factor equal to 0 and use quadratic equation to solve for it, we would get a complex root, 2 plus or minus 3i. Okay, so that brings us to conjugate pair theorem that says a plus bi is a root of a function. If a plus bi is a root of a function, then a minus bi is a root of the function. So a plus bi and a minus bi, complex roots always come in pairs. So that's going to be super helpful to us. Okay, so it says find the remaining zeros of f of x given that f of x is degree 6 with zeros at I, 3 minus 2i, and negative 2 plus I. Well, if I is a root, then negative I must also be a root. If 3 minus 2i is a root, then 3 plus 2i must also be a root. If negative 2 plus I is a root, then negative 2 minus I must also be a root by conjugate pair theorem. And that gives us 6 roots. It's degree 6, so we can't have any more, and those must all have a multiplicity of 1. So those are our remaining zeros just by conjugate pair theorem. All right, it says form a polynomial f of x with real coefficients. Now this is going to be important because look at the roots they're giving us. They're giving us complex roots, but they want a polynomial with real coefficients, having the given degree and 0. Okay, so it says it's degree 4. We've got a 0 at I, which means we must also have a 0 at negative I. We've got a 0 at 1 plus 2i, which means we must also have a root at 1 minus 2i. And that's 4 different roots, and it's a degree 4 equation, so we can't have any more, and they must all be a multiplicity of 1. Okay, that means my function looks like x minus I. X minus negative I would be x plus I. X minus 1 plus 2i. And notice that I put that in parentheses. We're still subtracting the entire root. Okay, and so we're going to have to distribute that negative to both parts. And then x minus 1 minus 2i, 1 minus 2i, again in parentheses. Okay, now that is a polynomial, but it doesn't have real coefficients. So what are we going to do to get those real coefficients? Well, these complex roots were solutions to irreducible quadratics. So all we have to do is remultiply them together, and then we'll get those real coefficients. So let's give that a try. So I'm just going to FOIL this out, or just distribute this x times each of those. That's going to give me x squared plus xi. Okay, now I'm going to distribute the negative I. That's going to give me negative xi, negative I squared. Now, what is negative I squared? We know I is the square root of negative 1. If you square both sides of that equation, I squared, squaring undoes the square root, so I squared is negative 1. So here we have negative I squared, so negative 1 is going to be positive 1. Okay, so that is just distributing and that first 2 factors. Okay, so let's keep going with the next 2 factors. Okay, so let's distribute this. First, I'm just going to distribute the negative x minus 1 minus 2i, and then x minus 1 plus 2i. Okay, so not a lot of work done there. Okay, as we move to our next step, positive xi and negative xi cancel. So this gives me x squared plus 1 is what the irreducible quadratic that those first 2 factors generated. Okay, now let's go ahead and try this next one. We've got to distribute the x to every term. Everything in the first parentheses multiplies by everything in the second parentheses. So in that first one, distributing the x times x is x squared, x times negative 1 is negative x times 2i is 2xi. Now we're going to distribute the negative 1 times each term. So negative 1 times x is negative x. That's going to be positive 1, negative 2i. Okay, now I've got to distribute the negative 2i times each thing. So that's going to give me negative 2xi. That's going to give me positive 2i. And that's going to give me negative 4i squared. Negative 4i squared. And we said I squared was negative 1. So negative 4 times negative 1 is going to be positive 4. Okay, and let's see if that cleans up. So we've got our x squared plus 1. And then what do we have? 2xi and negative 2xi, negative 2i and positive 2i. Okay, so that gives me x squared minus 2x plus 5. Okay, so there's our function with real coefficients. We could multiply that out again further if we wanted to, but really getting rid of the complex roots was what we were after here. So we can use our algebra skills. They work the same with complex numbers as they do with other numbers, a little bit of work, but we can totally multiply those complex roots out and get the factors that had real coefficients, those irreducible quadratics. All right, so it says use the given zeros to find the remaining zeros of each function. Now they gave us a hint here, okay, and so it's just because I want to show a different term. So the hint is to use synthetic division. Now we wouldn't have to use synthetic division. We've got zeros at 1 plus 3i, use the given zeros to find the remaining zeros. Okay, which means we also have to have a root at 1 minus 3i, and those aren't all the roots, but we're going to use those roots to help us find the remaining. Okay. So I could do what we just did, do the x minus 1 plus 3i and x minus 1 minus 3i, multiply it together, and get an irreducible quadratic. Then I could divide this polynomial by that irreducible quadratic. So that is one approach. But my hint here to use synthetic division, even though it's going to be a little ugly in the first step, I think you'll actually like it and think it's faster. Okay, so we're going to try synthetic division here just so that we can show you that that is an option. And once you get comfortable with it, I think you'll still think it's faster than multiplying the factors out to get a polynomial that you can then do long division by. So I think you'll like synthetic division more, but let's see how it works because it's definitely more involved. Okay, if we're testing 1 plus 3i as a root, then that's what goes to the box, okay? And we need the coefficients of our polynomials. So we've got 1x to the 4th, negative 7x cubed, 14x squared, negative 38x's, and negative 60. Okay, so we bring the first term down as is, 1, multiply it by our root, 1 plus 3i. So that's going to give me 1 plus 3i. Now, when we combine this, we're combining the real parts. Negative 7 plus 1 is negative 6, and then we're combining the imaginary parts, 3i. Okay, so now we're going to be multiplying this by our root, 1 plus 3i. So if I do this, and a lot of times I'll do a little parentheses here to help me keep my terms before I have to combine them. Negative 1 times negative 6 is negative 6. 1 times 3i is 3i. 3i times negative 6 is negative 18i. So negative 18i and 3i will make negative 15i. And then 3i and 3i is going to be 9i squared, which is negative 9. Okay, when I combine those like terms, that's going to give me negative 15 minus 15i. So again, this was just an intermediate step, so that's not part of our thing. We're just combining the 14 with the negative 15 minus 15i. So that's going to give me negative 1 minus 15i. Okay, and then I'm multiplying that by 1 plus 3i. Again, you can do the intermediate step if you like it. Okay, that's going to give me negative 1. That's going to give me negative 3i, and negative 15i is going to make negative 18i. And then 3i and negative 15i is going to make negative 45i squared, which will be positive 45. Okay, so that's going to be 45 minus 1 is 44 minus 18i. Okay, so again, that was just my intermediate steps. I'm going to mark it out. Negative 38 and 44 is going to be 6 minus 18i. Okay. Now I'm going to multiply it by my root. Okay, so again, I can do my intermediate step if I like that. Okay, so 1 and 6 is 6. Okay, that's going to give me 18i and negative 18i, which cancel each other out. And then 3i times negative 18i is going to be negative 54i squared, which negative 54i squared is positive 54. Now look what just happened here. 6 plus 54 is 60. We expected this because negative 60 and 60 is 0, and that gives us a remainder of 0, which is what we needed to have happen because we knew that this was a root of it. If it wasn't 0, we would know we had a mistake in our synthetic division here. So we knew it was a root. We expected it to have a remainder of 0. Okay, now this feels pretty intense, but I promise you you're going to love it in this next step. Because when I go now and divide those coefficients by my second root, 1 minus 3i, okay, it's conjugate pair, these are going to clean up and be much nicer. So I bring the first term down as is, multiply it by the root, that's going to give me 1 minus 3i. The negative 3i and 3i cancel, I get negative 5. Negative 5 times 1 minus 3i is going to give me negative 5 plus 15i. The negative 15i and positive 15i cancel. That gives me negative 6. Negative 6 times 1 minus 3i is going to give me negative 6 plus 18i. The negative 18i and positive 18i cancel. The 6 and negative 6 cancel, and I have a remainder of 0, which we knew we would because we already knew 1 minus 3i was a root. Now, so what we have here now is the remaining polynomial, x squared minus 5x minus 6. So if we keep going to continue factoring, now we want to switch and try this by hand. It's going to give me x and x. We're going to be negative 6 and positive 1. Okay, and that's going to give me my remaining zeros. Okay, so the remaining zeros are, let's do a list of all of them. So we had 1 plus or minus 3i, and then we had negative 1 and positive 6. Okay, so those were our zeros. Those were all of our zeros for that polynomial. Okay. So now just because we have these fancy tools doesn't mean that they're all going to be that hard. If we take a look at this polynomial, it says find the complex zeros of the polynomial. Okay, so remember, we just now have a box full of factoring tools. When I take a look at this one, I see that x fourth can break down to x squared and x squared to give me that middle term that's going to be x squared. So that's going to just be plus 9 and plus 4. 9 times 4 will make 36 and give me a middle term of 13x squared. Now, for each of those, when I set those factors equal to 0, I can just do this by hand. I don't need any extra fancy tools. So that's going to give me x squared equals negative 9. So x equals plus or minus the square root of negative 9, which of course means x equals plus or minus 3i. Okay, same thing over here. X squared equals negative 4. We undo a square with a square root, which picks up the plus or minus option. Don't forget that, or you'll miss half your roots and zeros, which means x equals plus or minus 2i. Okay, so the complex zeros of this, and of course there's that conjugate pair with the plus or minus 2, so that's where that comes from. That's why they always come in conjugate pairs. So we would say x equals plus or minus 2i and plus or minus 3i. Okay, so not all will be that hard, still using our other factoring tools when we have them. Now, a quick true or false. F of x is a polynomial of degree 3. These coefficients are real numbers, and its zeros are 2, I, and 3 plus I. True or false? Well, it's degree 3, and we have 3 roots here, but 2 of them are complex, and they don't have their conjugate pairs. We know if I is a root, negative I has to be. If 3 plus I is a root, 3 minus I has to be. So this one currently is false because that would generate 5 roots, and if it's degree 3, it can only have 3 roots. So it says, what could we do to make it true? Change it to degree 5 would work. There are other options as well, but that was one option that we could do to fix it. Change it to degree 5. Then it could have 5 solutions, which this one must. Okay, and then we're going to end with a challenge problem. So let's just try a little algebra here. So it says the roots of the equation 6x cubed plus kx squared minus 5x plus 6 equals 0 are 0.5 or a half, 3, and r. Find k and r. So we've got 2 unknown variables, and we've got to figure out how we're going to solve for it. One of the easiest ways to do this is to use the fact that we know that if 3 is a root, then we know f of 3 equals 0. So if we know that, basically we're saying that we can plug in the point 3, 0, and we know that it'll make this polynomial true. So let's try that. So if we put 0 in y's position, and here they already have it set equal to 0. So if we plug 3 in x's position, 6 times 3 cubed plus k times 3 squared minus 5 times 3 plus 6 equals 0. 3 cubed is 27 times 6. 162, is that what you got? Yeah, okay. And then 3 squared is 9, so we've got 9k minus 15 plus 6 equals 0. Okay, so then that, if I combine like terms, that gives me 9k, 162 plus 6 would be 168 minus 15, 153 equals 0. Okay, so negative 17. Okay, so k equals negative 17, just by using the fact that we knew that if 3 was a root, then 3 was also a 0 of the function, made the equation equal to 0, so substituted it and solved it. Now we have k, so now we have the remaining coefficient. So we now know that the coefficients of the equation are 6, negative 17, negative 5, and 6. So if 3 is a root, we need to find r, which is the remaining root. Okay, so let's use the fact that 3 is a root, and let's see what the remaining polynomial is, and we should be able to find that extra root. So that's my strategy. That's what I'm thinking here. Okay, so 6, 18, 1, 3, negative 2, negative 6, 0, which we knew it would be. So that gives me 6x squared plus 1x minus 2 is our remaining polynomial. Now, let me see what I've got here. So they told us 1/2 and 3. Okay, so if 1/2 is one of them, that's going to be 2x minus 1 for one of our factors. And so that would have to be 3x plus 2 would have to be the other factor. Now let me check and see. That's going to give me negative 3x plus 4x, which will give me the 1x. So yes, those are factors, okay? And I use the fact that it said that 1/2 was one of our roots to generate this factor, which helped me faster with the factoring here. So then if 3x plus 2 is our remaining factor, we can set that equal to 0 and solve for it, which gives me x equals negative 2/3. Okay, and that, I'm boxing it as x. I'm going to change that label to r. That's my remaining root. That's my remaining root of the function. So we've got k and r solved for there. Now that's not the only way to do it. There are other ways to do it. We could have done synthetic division with the k still as one of the leading coefficients and solved for k that way. But once we have it, we'd still want to plug it in and then find the remaining root, which we just did. All right, hope you enjoyed the challenge, working on those algebra skills.